we did normality practice. We reviewed the first 4, right? So we have 5, 6, 7, and 8 to do, right? All right, so just a reminder, we have exam on Monday. I'll cover this. So go to question 5. Opened up my R Markdown and get it up and going, and I run it. Hopefully you guys all have your R Markdown open, or the Markdown document. Formality, I'll let you get that open, get that ready. Here's mine, and hit run, and oops, I got a problem. Normality data not found. Why is that? Well, because I don't have anything loaded. So I have to go back. All the way up. Got to read in my data set again. Good thing it's in a chunk. Just run it. Load my car library. Now everything should be ready. So, question 5. Here's our histogram. All right. So, what do you think? Based on histogram, what would you say? Normal, non-normal? Yeah, I don't think it doesn't look normal. QQ plot, normal, non-normal, definitely non-normal. It's curved, very clearly curved. All right, and confirmed by Shapiro-Wilks. Gets super small p-value. So remember, 2.2 e to the negative 16. That's as small as R will calculate. So yeah, Q5 definitely non-normal. Q6. Run that. All right. Here's my QQ plot. What do you say? Normal, non-normal, maybe, either way. Yeah, it's kind of hard. And with these number of bars, it's kind of tough to judge whether it's normal or not. How about the QQ plot, though? What do you think? Normal, non-normal? What do you say, Alex? Cody?
I said normal.
You said normal. Who else says normal? I say normal. All right? All the points except 1 are in that 95% confidence interval, that envelope. And I said that it's okay if we have the extreme values fall out. All right? We just can't have an excessive number. We have one point fall outside of that line. If I had a second point, I'd still say this is normal. Right? I'd be okay with it. Be even better if we had 2 points, if it was 1 out there and then, maybe this one was out here. Right? So we had 1 at each extreme. I think that's okay. Most of our points here fall right in along our line. So right now our data appear to be normally distributed. Shapiro-Wilk also tells us that with our p-value of 0.89, 0.8864. But is this reliable? Is this reliable? Yes or no? No, why not? Why not? Look at our sample size. I could just see it in the QQ plot. What is that? 20 points maybe? 25 points? With that number of points, it's going to be very hard for Shapiro-Wilk to actually detect non-normality. So even though we know from the QQ plot that these data are normally distributed, Shapiro-Wilk will have a hard time detecting the non-normality portion of it. So with this few samples, few data points, definitely QQ plot. That's what we rely on. 7. What do you say? 4 bars, is that enough? No, definitely not enough. Why can't we add any more bars? I think we have a whopping 10 points here. All right. Is Shapiro-Wilkes going to be reliable? Not at all. All right. Even if these were like completely curved. So we got 2 points. So 1 point, 1 point, 1 point, 1 point, 1 point, 1 point. And then, I mean, when we look at it, it's like, yeah, that looks curved. Shapiro-Wilkes would probably still give us a p-value above 0.05. Just because we have 10 samples. So definitely rely on this QQ plot for these small sample sizes. Data appear to be normally distributed. And lastly, Q8, what do you say? Normal, non-normal? Histogram's kind of hard to see, right? Kind of hard to judge. So let's rely on the QQ plots. What do we say? Normal, non-normal? Normally distributed. All of our points fall right inside that envelope. The one exception is right up here at the end. Right, it's not at the very end. It's one of the outer points, but same concept. Almost all of our points fall along this line. We're good. We're normally distributed. Shapiro-Wilkes. We do have. I don't think we have. I don't know if we have 100 or not. And I don't think this tells us how many points we have. But we're kind of at number of points where maybe Shapiro-Wilkes will give us an okay interpretation, but again, since it depends on our sample size, it's probably better just to skip Shapiro-Wilkes and just go with QQ plots. All right. Any questions? So, these are all of our lines. Good thing we had that. The head. Were you getting the same figures as me? Yes? Okay, that's what I thought. So for some reason, my data set that was posted was different than what I actually used to make this graph, make the presentation. So this was that last question 8. So you can see that for some reason the data set got mixed up someplace along the line. But this is a good point. This looks curved, right? It looks S-shaped, all right? But would we conclude that it's normally distributed? Yeah. So Shapiro-Wilkes tells us, suggests that it's not. But a QQ plot, almost all of our points fall inside this envelope. I have a point here, maybe 2 points there, and 3 points out here. We're kind of on our threshold at this point. But because that confidence envelope captures almost all of our points, we would still conclude that our data are normally distributed and move forward. All right. If there was ever a question of whether or not we're normally distributed, then it goes to what statistical test we're actually using, and is that test robust against violations of normality? Like in ANOVA, it's robust. If we were questionable about this, I'd say just do an ANOVA, we're good. Right, same thing here. We've got those 2 points out, it's okay. I'd still say we're normally distributed. All right. Let's move forward. Anyone have parting questions? Right. Get this opened. And So we have, I don't really have a homework assignment where you can practice doing this because that whole normality practice, stuff was pretty extensive to kind of get your histograms. We walked through it. You should have plenty of examples for our exam. All right, but that up. I do have this. This is up. Oops. I guess I'm behind the edits. Optional homework, because our exam covers the probability stuff, and our exam will stop at our assessing normality. All right. I do have this extra probability problems. All right. Check the due dates. Due date says October 21st. What we're going to do is say on Monday it would be due. Since we'll meet in class at 11 o'clock, if you have questions about how to do some of these problems, you can either email me over the weekend or you can ask them in class at 11. These probability questions are just more questions related to probability, so independence, mutually exclusive type stuff, using addition rule, multiplication rules, Bayesian, another Bayesian test, Bayesian probability. This is using binomial or Poisson distribution, so going through picking out which probability or which distribution to use and then actually doing it. Now this says do it by hand, but we can use R, since everything's going to be on the computer, using the tables, calculating estimates for the binomial and the Poisson and stuff. So if you can sit down, if you sit down tonight or maybe on Saturday or Sunday to work through it and you find this worksheet pretty easy, I think you're going to find like these types of problems on the exam pretty easy. All right, so that's posted. I'll transition this. I'll make this also like an assignment that you can upload your documents. So if you do it in a Markdown, that'll work. And what I might do is just, since I have the Word document, I might just copy and paste it into a Markdown file, and then you can do your chunks that have the code in there if you want it, or you just write your answers. And with this optional homework, you don't have to do it, but if you do it and you have already missed the homework assignment, what I'll do is take this assignment as the replacement for it. That way we don't, it counts as a missing or incomplete. So I want to point that out. All right, hypothesis testing. We're going to move on to do stuff. Got to plug ahead. And honestly, I don't know. I feel like I'm behind now because I know this material was on the second exam. But another part of me suggests that our exam was in one more week, but I don't know that. I can't say that. All right, so introduction to hypothesis testing. We're going to introduce a bunch of terms related to this and kind of go over the idea, the concept behind hypothesis testing using some of this probability theory that we've been learning. All right, so why do we do hypothesis testing? We do it because we're interested in determining if things are different from each other. We have to do that because we have variation in our data. Anytime we repeat a experiment, we can get a different set of data, different numbers. Our averages are going to change and they're going to vary from one experiment to the next. So the statistics will allow us to control for that variation and determine if our overall averages are different, or perhaps if our overall medians are different. We're not really going to do variances, but we will have a variance test that we'll use. Tests, plural, that we'll use. All right, so when it comes down to hypothesis testing, we have to choose the correct type of test. That test is going to come down to what type of data we're working with. So is it normally distributed? Is it not normally distributed? Does it follow binomial or Poisson and so forth? And it also depends on what hypothesis we're interested in. Are Are we comparing the means? Are we comparing the medians? Or are we comparing the variances? All right, in some cases, we don't really care about the means or the medians. We're just concerned, is it higher or is it lower? Is there a directional change and so forth? So these two things, the underlying data and the type of hypothesis, the type of question we're trying to answer determines what tests we have available to us. All right, so to kind of introduce you to this concept of hypothesis testing and how we develop the probabilities and kind of say, yeah, it's something is having an effect on our data, we're going to introduce this working example. All right, so we caught roaches. Roaches are abundant here in the buildings. If you haven't seen them, you will. They are out there, all right? Not the little black bugs out there, those ugly roaches that are speedy, all right? So we caught a bunch of them. We measured their wing lengths, all right? And we caught them in cabinets in Science 3. We do have the data. It's roachrandomdata.txt. That's posted on Blackboard, so you can download it and import it into R, all right? When we do that, we can see that the average wing length for the cabinets roaches is 7.8. The average wing length for the Science 3 roaches is 6.8. Now, I predict, or I think, that these lengths are different, and the reason I say they're different is because we have offices here in this building where people are leaving food and the roaches are just can feast on all of that candy and stuff. All the Coke that Dr. Strength has, it's going to crawl in and eat the remnants, and they're going to get bigger. All right, that's my hypothesis. All right, so our question is, are they actually different? So this is our working example. So how do we go about doing that? Well, we've got a couple different ways to do it. All right, with this test, we're going to come up with a null hypothesis first. This null hypothesis assumes that there is no difference. All right, so just to kind of diagram this, our null hypothesis is going to be a specific statement that says, basically, something about the parameter that we're interested in. All right, so we have two roaches. We've got cabinets roaches, and we have Science 3. What we're going to do is come up with a null hypothesis that is interesting if it's rejected, and it tells something about the variable that we're interested in. We're interested in the means. All right? And as with almost all of our hypotheses, what we're going to assume is that these groups, these different buildings, actually belong to a population. The same population. And that population has a mean and a standard deviation associated with it. So if this is true, if both of these roaches, the roaches from cabinets and the roaches from Science 3, belong to the same population, then our null hypothesis will be that our means are equal. It's a very specific statement. It is talking about a variable that we're interested in, which is the mean wing lengths. And if we reject this, it's interesting. Because if we reject it, then we know that, no, these are not the same population. They're actually two separate populations. All right? Our alternate hypothesis is going to be that second choice. So if this isn't true, then what's our alternative? And in a lot of cases, our alternative is simply that they're not going to be equal. That they don't belong to the same group and thus they're not equal. All right? It could be that one is larger than the other. All right? We can do that as a null hypothesis. That's going to affect something later on. All right? So from the null and the alternate hypothesis, we will generate a test statistic that reflects this assumption, that affects our assumption that they all belong to this same population. All right? This test statistic is going to be some sort of calculated value, some quantity that's calculated using our data. And that value is then going to be compared to all of the possible values that we can get if this null hypothesis is true. So just for the sake of this example, let's assume our test statistic, TS, is the difference in our means. Let's assume that we picked a test statistic that is the difference of our mean. Well, we have an observed test statistic. That's our observed test statistic. That's just one of all the possibilities that we could have obtained. Because if we go out and repeat the sample, we're going to get a different test statistic. If we repeat it again, we're going to get a different test statistic. So what we do is we have our actual observed test statistic. We are going to compare it to all of the possibility of our test statistic if these all belong to the same population. That all possibilities, under the assumption that this is true, is called the null distribution. All right? It's the null distribution. So what we'll do, running out of space, I don't know. Okay, so we have this, so we kind of have this population. So we have a test statistic. This is our null distribution. That's our null distribution. All right, we did a histogram of all of our possible values. Okay, cut off just a little bit. Let me redo this. Probably cut off too. All right. That's better. All right, so our null distribution, that's all possible values that we could get if we repeated it over and over and over and over again under the assumption that the means are actually equal. What we're going to do is to look at our observed test statistic and see where it falls in this histogram. So maybe we are right there. All right? Maybe we are right there. What we're interested in doing is saying, how likely is it that we would get this observed or something more extreme just by random chance? So what we would do is figure out this area under the curve. And that is our p-value. Because that represents the possibility of getting our observed value or something more extreme if our groups actually were equal. All right? If this probability, if this area is small, then we say it's extremely unlikely that we would get this just by random chance alone. And if it's extremely unlikely that we would get this, then we would reject our null hypothesis that they're equal and conclude that they're not equal, because that was our alternate hypothesis. If this area is actually large, then we would conclude that, yeah, it's possible that we get this just by chance alone. And therefore, our means are equal. All right? Now, the other side of it is that we said as extreme or more extreme. So if that's the value, the average value of our test statistic, and we're below that, our test statistic is below that average, the other thing we can do is look at the upper extreme and say, okay, well, we could be below it a certain amount, or we could be above it a certain amount. And that area is still the same. If we use both of these, that's a two-tailed test. And that corresponds to this condition. Because we don't know if one mean is going to be greater than the other, or we don't know which one's going to be greater than the other. If we only use one of these, what we've done is set up direction and said, we think this one is going to be larger, and thus we focus just on that. Now, what's our cutoff? What determines, something that's too big or too small? Well, we set our value at 0.05. All right? So 5% chance. That's going to be our cutoff. If our p-value is below 5%, we say it's too unlikely to get a value that extreme or more extreme, and thus something other than chance is producing our difference. And what is that? We probably have two separate populations. If our p-value is greater than 0.05, then we say, yeah, we could have gotten that by chance alone. We failed to reject that null hypothesis. All right. Any questions? Move this up. Sorry, I had the picture blocking some of that text, so we can get the rest of this text. All right. Know the definition of a p-value. This is our general approach. This is how we're going to do it. Does everything go this way? Basically, it does. Right? So with our tests, we have a couple ways to obtain a p-value. All right? And we're going to see some of these tests. So one test is an exact probability test. It's called an exact test because we are actually going to use the probabilities that correspond to the distribution of our variable. And we can calculate exact probabilities. So an example of this is flipping a coin. Flipping a coin follows a binomial distribution. If we flip a coin, let's say 10 times, and we get 2 heads, you can ask, is this a fair coin? All right? And in that case, let's move our image. Move up. This curve is our exact distribution. Probability of getting 1 head, 2 heads, 3 heads, 4 heads. All right? So this curve, oops, sorry. Let me get my cursor. This curve represents our null distribution. Now, our null distribution is that, or our null hypothesis is that the coin is fair, right? The probability of flipping a head is 0.5. That's our null distribution. Under that assumption, this is our null distribution. We see 2 heads. So now what we want to do is calculate how likely is it that we would get 2 heads or something more extreme. So 2 heads, 1 head, or 0 head. And since we just asked the question, is the coin fair? We also have to do the flip side and say, well, what's the likelihood of getting 8 heads, 9 heads, or 10 heads? So our p-value ends up being the area under the curve on both sides of these. And we calculate it exact because we know the exact distribution. We can do it using p by num. All right? And again, don't worry about, I have the code here for the curve. I have the code to actually calculate the probabilities. All right? This is called the binomial test. So in this case, is the coin fair? Yeah, that's our p-value. It's 0.1. It's greater than 0.05. Thus, we failed to reject our hypothesis. In some cases, we might not know the exact distribution of our variable, but we have such a small sample size that we can figure out all possible combinations. So let's say we flipped coins again, but this time we only did 5, and maybe we don't have a computer and can't do the p by num function. Well, we just figure out all of our possibilities. These are all possible combinations of flipping a coin 5 times. And let's say we flipped 4 heads out of 5 flips. Well, if we want to ask, is this a fair coin? We want to look and count up how many ways is as extreme or more extreme. And that's 4 heads and 5 heads, or 4 tails and 5 tails. Then our p-value is just 4. There's 4 combinations, 4 possibilities, divided by our total number. There's our p-value. In some cases, we don't have that luxury. We can't enumerate it. It's not an exact test. So how do we approach it? Well, to approach it, what we can do is do a randomization test. This randomization test could be called a Monte Carlo simulation. Monte Carlo is that famous game, right? Just randomization. So in our randomization test, we assume that our groups are the same. And then what we do is shuffle up and randomly assign our groups and then calculate our test statistic. All right, so if we had our roaches, and let's say we had a deck of cards and we said the red cards are cavernous roaches and the black cards are science 3 roaches. All right, what we would do is shuffle them up and then reclassify them. So on the first shuffle, we'll deal half of them to one side, said these are all the cavernous, these, and then half to the other side, these are science 3, calculate our test statistic, and do it over and over and over and over again. Well, that randomization, all of those individual test statistics gives us our null distribution under the assumption that there was no grouping to begin with. We just arbitrarily assigned the groups. Then from there, with that test statistic, we look at our actual observed test statistic and says, well, where does it fall on this distribution? And how many more points exceed that value? All right, so this is a demonstration of these randomization tests using the Roach data. In our data set, our average for cavernous is 8.1. The average for science 3 is 6. We already said what our null distribution is. And in this case, our test statistic is going to be the difference in our wing lengths. So the cavernous minus the science. So if these are actually equal, then the difference in those means should be equal to 0. And that's going to give us a very good curve to look at. All right? So here's a randomization test that I ran. Don't worry, you don't need to know it yet. All right, we will go through this. But what I do is I took our sample, our roaches, I drew a random sample out of them. These are random wing lengths. And then from that random sample, I assigned cavernous and science 3 to them. So some of the roaches from cavernous are now grouped in science 3. Some of the science 3 roaches are now grouped in cavernous. Then I calculated the difference and saved it and did that here 1,000 times. And here's our histogram. This is the histogram of all of those randomized wing lengths. That histogram itself is our null distribution. All right? So how do we get a p-value? We compare our observed test statistic to that null distribution. And I want to point out, I overlaid a normal curve. Does this appear to be normally distributed? No, it's not. All right? It's not normally distributed. But that's fine, because these randomization tests didn't need our data to be normally distributed. And that's the beauty of these things. So in our test, we have our test statistics. That's our null distribution. And then the blue lines represent our observed test statistic. So we have an observed difference. We didn't set up a direction, so we have to go below and above. So if our difference in cavernous and science 3 was 2.1, I believe, all right, we have to go 2.1 units below our 0 and 2.1 units above our 0. And that region is the region that gives us our p-value. So those regions are what I call the rejection regions. If we have a test statistic, actually, our rejection regions represent the 5% tail region. So what I believe I've done here is that blue region represents 95% of all of our values. This is our 95% confidence interval. The tails have 5%. So our 0.05, our cutoff, that's what that refers to. So we have 2.5% here, 2.5% here. If we fall in that 5% region, we're in our rejection region. We reject our null hypothesis. If we don't, we're in our acceptance region. So we don't prove our null hypothesis is true. We've just failed to reject it. All right, so what do we have here? In our case, we have a value of like 2.1 or something like that. So what we have to do for our p-value is figure out how many of our randomized values equaled or exceeded that. And that's what my p-value here is telling it. So 5 values out of 1,001. 1,000 values that we randomly sampled, plus that one extra that we actually did observe. So our p-value for the Roche data is 0.006, which means we have a 0.6% chance that our observed difference in mean is due to random chance. That's too small to conclude that random chance produced that difference. Something other than chance did that. And what is that something? The buildings. Our classification. That is our difference. All right? Questions on this? I know I've gone through it. We're not really using R. It's just going through concepts. All right? Now, we're not always going to do these randomization tests. All right? We're not always going to do these randomization tests. For example, we're going to do a t-test. And there we go. All right, so with our t-test, we're doing the exact same thing. Or an ANOVA as well, but a t-test, we can read it. All right, so our t-test, exact same thing. We are interested in means. We are interested in if one mean is equal to another mean. All right, and then our alternate can be that they're not equal. For our t-test, our test statistic is actually a t. All right, and the t is the difference in our means divided by the standard error of our difference. All right, and we'll learn about this. All right, we'll learn about this. This is our t observed. All right, we're not doing a randomization test. But if all of our assumptions of our test are true, then this t follows a t distribution. That's going to follow a t distribution. So then what the t-test is going to do is says, okay, well, we have a hypothetical t distribution. We'll follow this if we've made all of our assumptions of the test. Where is our t observed? Where is our t observed? And what is the area under the curve that represents the more extreme values? So that and that is our p-value. And I'll put 1/2 of the p-value just to kind of emphasize that both together meet our p-value. So while I introduced this concept of hypothesis testing using a randomization test, a regular test that we'll learn, t-test, ANOVA type stuff, does the same thing. It just, our assumptions of the test allow us to assume that our test statistic follows a known distribution. If we don't follow if our assumptions aren't true, what do you think happens? What do you think happens? Anybody? We would do a t-test for these roaches. Do you think we followed a normal distribution for our data? Probably not. So what happens to our test statistic? It no longer follows our t-distribution in this case. So that's one of those things. If we violate our assumptions, one of the things we can do is do a randomization test, because it makes no assumptions and we generate our own null distribution. All right. So with these tests, move that down here, it goes back to our Bayesian statistics setting. So Bayesian statistics, we have a condition, we either have it or we don't, and then we had a test that detects that condition. And sometimes we identified it correctly, sometimes we didn't. the same sort of things happen with our statistical tests. Either our samples are not true to begin with, and our null hypothesis is wrong, or it's correct. And what we're trying to do with statistics is correctly reject it when we should, or correctly fail to reject it when we should. All right? So, errors are when we make those mistakes. A type 1 error is when we reject our null hypothesis even though we shouldn't reject it. So it's a situation where we have our means being equal and we conclude that they're not equal, but in fact they are. All right? A type 2 error is kind of the opposite. Now, we fail to reject our hypothesis when we really need to reject it. All right, so our null hypothesis is wrong, but we don't get a p-value that allows us to say that it's wrong. That's a type 2 error. All right, so type 1 is we reject it when we shouldn't. Type 2 is we fail to reject it when we should. When we should reject it. Now, our type 1 error is going to be set. We set the type 1 error. All right? And the error level that we set for this type 1 error is 0.05. That whole 0.05 level is arbitrary. We've made it up. A couple guys sat around a table drinking a beer, because we know that back then it was probably just male-dominated world, right? Even though the brilliant minds. Actually, hold on. Have you seen Warehouse 13? Older sci-fi series. You guys were probably middle school maybe at that time. Maybe. But they had H.G. Wells in that show. H.G. Wells was actually a woman, and it was her brother who was the author, inventor, when it was actually her, but that was the front end because of the society. So when I say a bunch of guys sitting around, no harm there, but they were sitting around and said, okay, well, what do we need our cutoff at? And they're like, well, here's 5%. All right. Why was it 5%? Who knows? They set it at 5%. So that's actually our type 1 error rate. That's our alpha level. That's going to be what we set and say, okay, 5% is going to be our cutoff because we think at 5%, it is so unlikely that chance gives us that level that we're going to reject our null hypothesis. That's all it means. Right? That's our alpha. All right. Beta is our type 2 error rate. Now here's the thing. We set alpha ourselves. The actual beta depends on the true null distribution. So we make an assumption of a null distribution, but we don't know what the actual one is. The actual distribution determines our beta, that probability of the type 2 error rate. All right? So what are all of the relationships? And I think once we do this, we'll be ending. Where's my present? Oh no. What time is it? So it's on another presentation. I'll have to download it. So I think what we'll do is we'll do this on Monday. So it says see diagram. I have a diagram that's in a presentation, so that way I don't have to draw it out. It's there, you can see it, and you'll be able to draw it out on your own. But know this, if we increase our alpha, if we decrease our alpha level, if we make it harder for us to make that type 1 error, we're going to increase the chances of making that type 2 error, and vice versa. So if we're really concerned about committing a type 1 error, we're going to increase our chance, and we fix that by lowering our alpha and saying we're going to set our cutoff at 0.01 instead. What we're going to do is increase our beta. If we're concerned about committing a type 2 error, all right, and we say we need to really be careful about that, then what we're going to do is increase our type 1 error. So that's the next slide that kind of shows that. As alpha increases, or as alpha decreases, B increases, and vice versa. All right, so we'll look at this diagram on Monday. And I don't know if Warehouse 13 is on Netflix or not. We finished that up, and now we're watching The Librarians, which is also another older show. And I want to say, hold on. Cody, what year were you born? If you don't mind me asking.
98.
98? Middle school was probably very generous unless you progressed through school very quickly. Y'all were probably in grade school when Warehouse 13 was on. Yeah. So, all right. You guys have a good